Hi, welcome back. In part three of It's a Small World, I'm going to be unraveling the science behind ionic bonds, hydrogen bonds, and van der Waals interactions. Just as a refresher, in part two, I discussed one method that atoms use to become chemically stable, and that's by sharing electrons with other atoms and thus forming covalent bonds with them. Atoms can also become chemically stable by either gaining or losing electrons. Let's take a look at this concept by exploring an interaction between a sodium atom and a chlorine atom. So as you can see right here, the sodium atom's valence shell is the third electron shell, and it has one valence electron. Meanwhile, this chlorine atom's valence shell is also its third electron shell, except it has 7 valence electrons. So the sodium atom is going to donate its one valence electron to this chlorine atom. The benefits for chlorine in this interaction are obvious because now chlorine's valence shell is full because it has 8 valence electrons in its third electron shell. And as you may remember, the third electron shell can hold up to 8 electrons. Therefore, chlorine's valence shell is full and is now chemically stable. But what about sodium? This interaction seems kind of unfair to sodium, right? Well, don't worry. Sodium is also chemically stable now. Because think about it. It's going to be losing this electron right here, and therefore it'll have no electrons left in its third electron shell. Therefore, its outermost shell is now its second electron shell, right over here. And oh wait, 1, 2, 3, 4, 5, 6, 7, 8. Sodium's second electron shell is already full. So by losing this one valence electron, the second electron shell of sodium now becomes its valence shell, and that valence shell is already full. So hence, the sodium atom also becomes chemically stable through this exchange. But you have to remember that electrons are negatively charged. So normally, this chlorine atom would have 17 protons and 17 electrons. 17 minus 17 is 0. Normally, it would be neutrally charged. And normally, sodium would have 11 protons and 11 electrons. 11 minus 11 is 0. It would be neutrally charged. However, due to this interaction, chlorine is gaining an electron. So now it has 17 protons and 18 electrons. 17 minus 18 is -1. So chlorine is now what you call an anion, which basically just means a negatively charged atom. And then sodium, because it's losing this electron right here, it now has 11 protons and 10 electrons. 11 minus 10 is 1. So now sodium is positively charged, and it's called a cation, which just means a positively charged atom. Now, you may have heard the saying that opposites attract, and that's the case in science too, because now that this cation, the sodium cation is positive, and this chlorine anion is negative, they'll attract and form a bond called an ionic bond with one another. And by the way, the formation of an ionic bond between sodium and chlorine leads to a compound that I'm sure you're all too familiar with, table salt. Now that we've discussed the two strong bonds, let's take a look at some of the weaker attractions. Now, don't associate the word weak with unimportant because the next two bonds I'm going to talk about are, yes, they are weak, but they are very, very important to life. So let's go back to our water molecule example. So here we have one oxygen atom covalently bound to 2 hydrogen atoms. And because these are polar covalent bonds, this oxygen atom right here is partially negatively charged, and each of these hydrogen atoms are partially positively charged. So a hydrogen bond, which is the first type of weak attraction that I'll be talking about in this video, forms between the partially positive portion of one molecule and the partially negative portion of another molecule. So let's take 2 water molecules, for example. A hydrogen bond could form between the partially positive hydrogen atom of one water molecule and the partially negative oxygen atom of another another water molecule. As you can see right here, one water molecule has the potential to form 4 hydrogen bonds at once. Now, hydrogen bonds, though they're constantly forming and breaking, are super, super important to the properties of water. But water deserves its whole own video, so I'll elaborate on that in a future video. The final type of attraction is called van der Waals interactions. So I took AP Biology last year, and for the purpose of AP Biology, you really only needed to have a very, very simple understanding of what van der Waals interactions are. So I'll be teaching you what you need to know about van der Waals interactions for AP Biology. So Electrons are always moving in an atom. And sometimes what can happen is that all the electrons in an atom, or most of the electrons in an atom, can be concentrated on one side of the electron, as shown right here. So what's going to happen is that one side of the electron will have a negative charge, while the other side of the atom will have all the protons concentrated there, and thus it will be positively charged. If this atom right here comes close enough, like 5 nanometers or less, close enough to another atom that is undergoing a similar thing, where it has all the electrons concentrated on one side of the atom and the protons concentrated on the other side, then they will form a van der Waals interaction with each other, because negative and positive, they attract. However, this is a weak attraction, unlike the ionic bond, because remember, electrons are always moving. So yes, they'll have an interaction for a bit because of the orientation of electrons in the atom, but soon the electrons will move again, and this atom right here will start to look like this, and this atom right here will start to look like this, and they won't really attract with one another anymore. Well, that's all for this video. Hopefully I helped you unravel some of the smallest parts of our world, which are arguably more important than the larger parts. Hope that helped. Thank you.